All right, folks, strap in. We're going deep today. You've hit us with 6 Easy Pieces by Richard Feynman.
Oh, classic.
Yeah, and we're going to unpack it, break down these
To
chapters.
dive in.
Yeah, explore this mind-blowing world of physics. Right now, you might be thinking, easy physics.
Yeah, right.
But trust me on this, Feynman. He had this incredible way of explaining, like, even the most complex ideas.
Oh, yeah, he could break it down.
Yeah, in a way that anyone could grasp, really.
Yeah.
He hated jargon,
Oh, he hated jargon.
and he just loved using simple, like, everyday examples to make science come alive.
And it worked. He was, what, a natural teacher, you know?
Yeah, absolutely.
What I find fascinating about Feynman, though, is his skepticism, like almost playful skepticism towards that rigid scientific formality. He just had this intuitive way of understanding nature.
Right.
And it really shines through in his writing.
Like he's inviting us along, right?
Yes, so
Explore,
does.
not just lecturing at us. So let's jump right in. Chapter 1, Atoms in Motion. This chapter goes right to the heart of it, right? The idea that everything, literally everything, is made of these tiny particles called atoms.
The building blocks.
I mean, think about it. Even you and I, we're just a collection of atoms constantly in motion.
It's mind-boggling when you really think about the scale of it.
It is.
You know, Feynman, he really brings this concept to life. Uses an analogy. Imagine magnifying a single drop of water to the size of the Earth.
Wow.
Okay, at that scale, the atoms would be about the size of apples, bouncing and jiggling around.
That's a pretty wild image.
Powerful image. Helps us wrap our heads around this sheer scale and dynamism of the atomic world.
Okay, that's seriously cool.
Right.
And then he goes on to explain solids, liquids, gases.
Yeah.
Not in, like a boring textbook way.
No.
But by connecting to something we all experience.
Right.
Water.
Mm-hmm.
So think about ice,
Place.
liquid water, and steam.
That's H2O, right.
All made of the same water molecules, but like their behavior, it changes drastically depending on how much those molecules are jiggling around.
Uh-huh. That's the key. That jiggling.
And that jiggling is what we experience as heat.
It's so simple, but so profound.
Yeah, right.
And from there, Feynman takes us deeper into chemistry. How atoms interact, bond with each other, form molecules.
Oh.
Oh, can think of it like a molecular dating game.
A dating game. Okay.
Certain atoms, they have preferences, for bonding with specific partners.
Oh, interesting.
Yeah, and this intricate dance of atomic attraction creates this incredible diversity of substances we see all around us.
I'm starting to see why this guy was such a beloved teacher.
Oh, yeah.
It makes you want to keep learning.
Absolutely.
He even breaks down something like salt dissolving in water.
Oh, yeah.
Paints this picture of sodium and chlorine atoms breaking away from the salt crystal, surrounded by water molecules constantly dissolving and rejoining.
Dynamic equilibrium.
It makes you realize even something as simple as, like, stirring salt into your soup, there's a whole hidden world happening.
Right. It's happening at the atomic level. It's a testament to Feynman's ability to find, the extraordinary in the ordinary.
Yeah, absolutely.
And, he doesn't just focus on individual atoms or molecules. In Chapter 2, Basic Physics, he zooms out, explores the fundamental principles governing the whole universe.
Yeah.
And this chapter introduces a key concept, amalgamation in science.
Amalgamation.
It's the idea that seemingly different phenomena can often be unified under a single framework.
So finding those hidden connections.
Exactly. Like, think about it. Heat and mechanics, seemingly totally different fields, right?
Yeah.
But both can be explained through the motion of atoms.
Oh, interesting.
And then there's this amazing unification of electricity, magnetism, and light. All different aspects of the electromagnetic field. It's this realization that the universe operates on these elegant, interconnected principles.
Bro.
Not just random events.
So hold on. I thought atoms were like protons, neutrons, electrons. Where does light even fit into all of this?
That's where Feynman's explanation of light as an electromagnetic wave comes in.
Okay.
He breaks it down. The frequency of the wave determines its properties.
Okay.
From radio waves to visible light to X-rays, all part of the same spectrum. Different vibrations, really, of the electromagnetic field.
Okay, I think I'm starting to see the connections here.
Right.
But then he throws us a curveball. Hints at the strange behavior of light at high frequencies.
Oh, yeah. He's setting us up, giving us a little peek into the world of quantum mechanics.
Where things get a little weirder.
A lot weirder.
Yeah, talk about a cliffhanger.
Right. Fasten your seatbelts, folks. And speaking of weird, in Chapter 3, The Relation of Physics to Other Sciences, he explores how physics is the bedrock of all the other scientific disciplines.
Okay.
His central argument is bold. Everything that happens in biology, chemistry, even astronomy can be understood through the lens of physics.
So he's basically saying physics is the key to understanding life itself.
That's the gist of it, yeah.
It's a big claim.
Bold statement, but he backs it up.
Okay, how so?
He uses a series of fascinating examples, like he delves into the Krebs cycle. You familiar with that?
Refresh my memory.
This fundamental process in biology provides energy to living cells. He shows how enzymes, these remarkable proteins, they act as catalysts. They're facilitating chemical reactions, lowering energy barriers.
Wait, enzymes are proteins?
Yeah, they're large, complex molecules made up of chains of amino acids.
Okay.
They're essential, carry out tons of functions in the cell, transporting molecules, catalyzing reactions, providing structural support.
So understanding them is, like, crucial to understanding life.
Exactly. And Feynman is connecting the dots, right, between this microscopic world of atoms and the macroscopic world of living things.
That's really incredible. But he doesn't stop there, does he?
Oh, no, he keeps going. He highlights another tool that scientists use to study biological processes. Isotopes.
Isotopes, okay.
These are atoms of the same element, but with different masses. Scientists use them as green marks to trace the path of atoms in complex reactions.
So it's like a molecular GPS tracker.
Exactly. Imagine being able to follow a specific carbon atom as it journeys through a plant during photosynthesis. That's what isotopes allow us to do.
That's amazing. We can learn so much about life by studying the physics of atoms.
We can. But there's a fundamental question here. We've talked about how enzymes help facilitate reactions, but what drives those reactions in the first place? What's the energy source?
Yeah, good question.
Well, that leads us to one of the most fundamental laws of physics, the conservation of energy. And this is what Feynman explores in Chapter 4.
Okay.
To explain this, he uses a brilliant analogy. Imagine a child playing with a set of indestructible blocks. Okay?
Indestructible blocks, right?
No matter how the child arranges the blocks, the total number of blocks always stays the same.
So the blocks represent energy.
You got it. Energy can take on many forms. Gravitational potential, kinetic, heat, elastic, electrical, chemical, radiant, nuclear, and even mass energy.
Okay, a lot of forms.
But just like those indestructible blocks, the total amount of energy in a closed system, it always remains constant. It can be transformed from one form to another, but it can never be created or destroyed.
So it's like this cosmic accounting system.
It is, making sure everything balances out.
How does this apply to, like, those chemical reactions we were talking about?
Think of it this way. Chemical reactions involve breaking and forming chemical bonds, and that requires energy.
Okay.
This energy can be absorbed from the surroundings,
right,
like heat, for example,
Uh-huh.
or it can be released into the surroundings. But the total amount of energy involved, including the energy stored in the chemical bonds, always stays the same.
It's amazing how this simple principle can explain so much, from planets to plants to machines.
It shows this underlying order to the universe, this balance.
Right. But if energy can't be created or destroyed, where did all the energy in the universe come from?
That's the million-dollar question. One that has puzzled physicists for centuries. One that we'll definitely need to explore further. But for now, let's shift our focus to another fundamental force: gravity. In Chapter 5, The Theory of Gravitation, Feynman takes us on a journey through the history and implications of this remarkable force.
Okay, I'm ready. I mean, gravity is something we experience all the time, every day.
Right.
But it's still kind of mysterious. What actually makes objects attract each other?
That's the big question, isn't it? Feynman begins with Newton's law of universal gravitation.
Okay.
It's this simple but profound equation,
Uh-huh.
describes the force of attraction between any two objects with mass. It states that the force is proportional to the product of their masses,
Okay.
and inversely proportional to the square of the distance between them.
So the more massive the objects, the stronger the attraction, and the farther apart they are, the weaker it gets.
That's it.
Okay, that makes sense. But how did Newton even come up with this law?
Well, Feynman tells the story of how Newton's breakthrough was inspired by Kepler's laws of planetary motion.
Okay.
Kepler had observed that planets move in elliptical orbits around the sun,
Right.
the sun at one of the foci of the ellipse.
Okay.
And Newton realized The force responsible for keeping planets in their orbits had to be directed toward the sun.
Oh,
not, tangentially, as was previously thought.
So observation and math led to this discovery.
It's a powerful combination.
It is. But did Newton have any proof? Like, did his law actually work?
Oh, absolutely. Feynman describes how Newton used his law of gravitation to predict the moon's fall. He calculated how far the moon should fall toward the Earth in 1 second based on the inverse square law.
Oh.
And it matched perfectly with the observed motion of the moon.
Wow.
It was a stunning confirmation, extending the reach of gravity from, the apple falling from a tree to the celestial dance of planets and moons.
Okay, that's pretty amazing. But does gravity only work on big things, like planets and stars?
It affects everything with mass, no matter how small.
Okay.
It's just that the force is incredibly weak for objects with small masses.
So that's why my coffee cup isn't flying towards my computer screen right now.
Exactly.
Okay, good to know. But if gravity's always pulling things together, why doesn't the Earth just fall into the sun or the moon crash into us?
That's where the concept of balanced forces comes in. You see, the Earth is constantly falling towards the sun.
We are.
But it's also moving forward at a high speed. This forward motion creates a centrifugal force that counteracts the inward pull of gravity, keeping us in a stable orbit.
So it's like a cosmic dance.
It is. Gravity and motion working together.
All right. What about the tides? I know the moon is involved somehow, but how does that work?
Feynman explains that tides are caused by the difference in the moon's gravitational pull on different parts of the Earth. The side of the Earth closest to the moon experiences a stronger pull than the side farthest away.
Right.
This difference in pull creates a bulge of water on both sides of the Earth, resulting in high tides.
So the moon is stretching our oceans.
In a way, yes.
That's powerful. So gravity's responsible for keeping planets in orbit, creating tides. Does it have any other large-scale effects in the universe?
Oh, absolutely. Feynman talks about how gravity governs the motion of stars in binary systems, where two stars orbit each other.
Right, right.
It also shapes the structure of globular clusters.
Globular clusters.
These spherical collections of, hundreds of thousands of stars.
Wow.
Held together by their mutual gravitational attraction.
It's incredible that this invisible force shapes the universe on such a massive scale.
It is,
Yeah.
But it also plays a role in the formation of stars themselves.
Really?
Yeah. Feynman explains how stars are born from these vast clouds of dust and gas. Gravity pulls these clouds together, causes them to collapse and heat up. Eventually, the temperature and pressure at the core becomes so high that nuclear fusion begins, and boom, a star is born.
So gravity is not just holding things together, it's creating stars.
Exactly. It's a force of creation as well as a force of attraction.
But there's one thing I'm still wondering about. We've talked about how gravity works, but what is it really? What's the mechanism behind it all?
That's the ultimate mystery. And Feynman points out that despite all we know about its effects, we still lack a complete understanding of how gravity works at its most fundamental level.
Interesting.
We have Newton's and Einstein's descriptions, which work incredibly well, but we still don't have a deep explanation of its underlying mechanism.
It's like gravity is this ghost, right? We can observe it, measure it, but its true nature remains elusive.
That's a great way to put it. And now we arrive at our final chapter for today. Quantum behavior. Get ready, because this is where things get truly bizarre.
Okay, hit me.
Feynman starts by setting the stage with a thought experiment. Imagine firing bullets at a wall with 2 holes, all right?
2 holes, okay.
The bullets, they're particles. Right. So they would either go through one hole or the other.
Makes sense.
Creating 2 distinct patterns on a detector behind the wall.
Okay, yeah, straightforward enough.
But now, what if we repeat the experiment, but with electrons? This is where things get interesting.
Okay, I'm intrigued. What happens?
With electrons, we observe an interference pattern on the detector.
An interference pattern.
Like the electrons are behaving as waves, not particles.
So they're going through both holes at the same time.
That's the strange thing. It's like each electron is somehow going through both slits simultaneously and interfering with itself.
That's wild. How is that even possible? It's like saying you can walk through 2 doors at once.
That's the beauty of quantum mechanics. It challenges our everyday intuition.
It definitely does. So how do we make sense of this? What's the explanation?
Well, in quantum mechanics, particles aren't really tiny billiard balls with definite positions and speeds.
Okay.
They're represented by something called wave functions. These are mathematical expressions that describe the probability of finding a particle at a particular point in space.
So it's not that the electron is literally splitting in half and going through both slits. It's more like its probability of being in different locations is spread out, like a wave.
Exactly. And when we try to measure which slit the electron goes through, we're essentially forcing its wave function to collapse into a single point.
Ah, I see. So observation is not just passively watching something, it's actively interacting with it and potentially changing its state.
You got it. And this leads to some really mind-blowing interpretations of quantum mechanics.
Like what?
Well, some physicists believe that reality is not objective, but rather shaped by the act of observation.
Wait, are you saying our consciousness, our awareness, could actually play a role in creating reality?
It's a profound and controversial idea, but even if we set aside the philosophical implications, it's clear that quantum mechanics isn't just some abstract theory. It has real-world consequences.
Okay, like what? How does it show up in our everyday lives?
Quantum mechanics is the foundation of modern technology. It underpins everything from the transistors in our computers and smartphones to lasers and CD players and medical devices. It even explains how the sun shines and how stars are formed.
So even though it's counterintuitive and weird, it's essential for understanding the world around us.
Exactly. Feynman saw quantum mechanics not as a set of abstract equations, but as a window into this strange and beautiful world of the very small.
And he had a knack for making it accessible, for explaining these complex ideas in a way that almost felt magical.
Absolutely. He had this infectious enthusiasm that made you want to learn more, to delve deeper into the mysteries of the cosmos. And that's what we'll continue to do in the next part of our depth dive.
Sounds good. I'm ready for more. Welcome back. My head's still spinning from that last chapter.
Quantum mechanics, yeah, it's a real head trip.
It challenges, like, everything you think you know about the world.
It does. That idea that particles can be waves, that just watching something can change it.
It's mind-boggling.
It is.
I'm still stuck on that whole wave-particle duality thing.
Mhm.
It's like trying to imagine a basketball suddenly becoming like a ripple in a pond.
Yeah, it's hard to visualize.
How can something be both a particle and a wave at the same time?
That's the core mystery of quantum mechanics. Remember that double slit experiment?
Yeah,
If electrons were just particles, we'd see two bands on that detector screen.
right.
But instead, we get that interference pattern, like they're waves.
Right, like each electron is going through both slits at the same time and interfering with itself.
Exactly.
It's like saying you can walk through two doors at once.
Well, that's where the concept of the wave function comes in. In quantum mechanics, particles aren't described as, tiny little balls with a definite position and speed.
Okay.
Instead, they're represented by these wave functions. And these are mathematical expressions that describe the probability of finding a particle at a certain point in space.
So it's not that the electron is physically splitting in half and going through both slits. It's more like its probability of being in different places is spread out like a wave.
That's a good way to think about it. And when we try to measure which slit the electron goes through, we're essentially forcing its wave function to collapse into a single point.
Okay, so the act of observing it changes it.
Exactly. It's like if you try to pinpoint the exact location of a ripple on a pond, the moment you touch it, it disappears.
So observation is not just passively watching, it's interacting. And that interaction can change things.
It can, and that leads to some really interesting interpretations of quantum mechanics.
Oh, like what?
Some physicists believe that reality itself isn't objective, but it's shaped by the act of observing it.
Whoa, hold on. Are you saying that our consciousness, like our awareness, could actually influence reality?
It's a mind-blowing idea and a controversial one. But even if we put those philosophical implications aside for a minute, it's clear that quantum mechanics is not just theoretical.
Right.
It has real-world applications.
Yeah, okay. What kind of applications? How does quantum mechanics actually affect our lives?
Well, for starters, it's the foundation of pretty much all modern technology.
Really?
Think about it. Transistors in our computers and smartphones, lasers and CD players, medical imaging devices, even things like how the sun shines, how stars form, it all comes back to quantum mechanics.
So even though it's counterintuitive and strange, it's crucial for understanding the world around us.
It is. Feynman had this amazing way of seeing quantum mechanics, not as these abstract equations, but as a window into this bizarre, beautiful world of the very, very small.
And he was so good at explaining it, making it feel almost magical.
He was, and he had this contagious enthusiasm,
Yeah.
Made you want to learn more, dig deeper into these mysteries of the universe.
Yeah, yeah. While we were talking about gravity earlier, something Feynman said in the book popped into my head.
Oh, what was that?
He was talking about how even with all our scientific advances, we still don't really get how gravity works at the most basic level.
Right. We have Newton's laws, Einstein's theories.
Yeah.
They describe gravity's effects perfectly, but that underlying mechanism, the how of it all, is still a big question mark.
It's like gravity is this invisible thread connecting everything, but we can't see the thread itself.
It's a great analogy.
Makes you wonder, are there other forces out there, forces we haven't discovered yet, that could explain things like dark matter, dark energy?
It's a fascinating possibility. After all, we've barely scratched the surface of the universe's mysteries. There could be whole new areas of physics waiting to be uncovered, new particles, new forces that change everything we think we know.
It's both humbling and exciting at the same time, right?
Yeah.
Like, we know so little, but there's so much potential for discovery.
Exactly. And that's what makes science so captivating. I think Feynman would agree. He always emphasized that it's not about finding all the answers, but about asking the right questions.
That's a good point. It's about staying curious, keeping that sense of wonder alive.
Absolutely. And Six Easy Pieces really embodies that spirit. It gives us this glimpse into the fundamental laws of the universe, but it also leaves us with this desire to explore further.
Yeah. I mean, this whole deep dive has been a reminder that science is a journey, not a destination.
It's about constantly questioning, refining our understanding.
And being open to new ideas, new discoveries.
Embracing the unknown, never losing that childlike curiosity.
And sometimes those questions lead us down these unexpected paths, revealing these hidden connections, this beauty in the most ordinary thing.
Like that salt dissolving in water.
Exactly.
Who knew something so simple could be so complex at the atomic level?
It's like the universe is full of these little secrets, these surprises just waiting to be uncovered.
And that's what makes learning so rewarding. It's this constant process of discovery, of uncovering the patterns that connect everything.
Well, as we continue our journey through 6 easy pieces, I have a feeling we're in for a few more surprises.
I think you're right. We've covered the building blocks of matter, the fundamental forces, even dipped our toes into the quantum realm.
But there's still so much more to explore.
Absolutely. Who knows what mysteries we'll uncover as we delve deeper into Feynman's brilliant mind. Stick around for part 3, where we'll tackle the remaining chapters and continue our deep dive into the fascinating world of physics.
Welcome back to the deep dive. Exploring the world through Feynman's eyes is it's like getting this fresh perspective on everything.
Oh, it really is. He had this unique talent for cutting through the noise and showing you the elegant simplicity at the heart of these complex ideas.
Yeah, absolutely.
No wonder so many people were drawn to his way of explaining things.
And inspired by him.
Absolutely.
It's like, I'm struck by how much we've already covered.
It's been a lot.
From those jiggling atoms that make up, well, everything around us.
Right.
To that mind-bending world of quantum mechanics.
It's been a wild ride.
It has. But what's really cool is that Feynman, he never loses sight of the bigger picture. He connects these seemingly totally different ideas.
He does.
And shows how they all fit together to paint this grand picture of the universe.
Yeah, that's the beauty of it.
When we were talking about gravity earlier, I kept thinking about something Feynman said in the book about how, despite all our scientific progress, we still don't truly get how gravity works, at the most fundamental level.
It's true. We've got Newton's laws, we've got Einstein's theories. They describe gravity's effects incredibly well.
Right.
But that underlying mechanism, the how of it all, it's still a puzzle.
It really is. It's almost like gravity is this invisible force that acts across huge distances, but without any, physical connection.
Like a cosmic puppet master pulling the strings, but we can't see the strings.
Exactly. And it makes you wonder, right?
Yeah.
Could there be other forces out there, forces that we haven't even discovered yet?
Oh, possibly.
That govern the universe at scales we haven't even thought to look at.
Yeah, scales beyond our current comprehension.
Forces that could maybe explain some of the biggest mysteries in physics.
Like dark matter.
Dark energy.
Exactly.
It's kind of a mind-blowing thought, isn't it?
It is. It makes you realize how much we still don't know.
Yeah.
How much is still out there to be discovered.
It's humbling, but it's also exciting.
Oh, absolutely. It means there's still so much more to learn, to explore.
And I think that's a perfect way to wrap up our deep dive into 6 easy pieces.
I think so, too.
It's given us this incredible glimpse into the fundamental laws that govern the universe.
Nice.
But it's also left us with this sense of wonder and a real thirst to keep exploring.
That's the beauty of science, isn't it? It's a never-ending journey of discovery.
It is. It's about asking questions, challenging what we think we know.
And being open to those new ideas, those unexpected discoveries.
Yeah, and sometimes those questions, they lead us down these paths we never expected.
Oh, for sure.
And they reveal these hidden connections, this beauty in the most ordinary
Like
things.
that salt dissolving in water, right?
Exactly.
Simple, everyday phenomenon, but when you look closer, it's this incredibly intricate dance of atoms and molecules.
So to everyone listening out there, I encourage you, keep exploring, keep asking those questions,
Keep that curiosity alive.
keep Feynman's spirit alive. Who knows what incredible discoveries are waiting for us in the future?
And if you ever find yourself feeling lost or overwhelmed by it all, just remember Feynman's words. The pleasure of finding things out.
That's what it's all about.
So go out there and find your own piece of the universe to explore. Keep diving deep.
Until next time.